Ever wondered how GPS finds the quickest route to your destination? Well, it's all down to a fascinating area of mathematics called shortest path problems. It's a problem-solving method used to determine the shortest possible route between 2 points on a graph, digraph, or network. This might sound technical, but it has real-world applications you encounter every day. From navigation systems like your GPS, to delivery services figuring out the quickest way to get your pizza to your doorstep, shortest path problems play a crucial role. There are several ways to solve these problems, but today we'll focus on 2 main methods: determination by inspection and Dijkstra's algorithm. Both are powerful tools in understanding and solving these problems in a variety of contexts. In the next few minutes, we'll dive deeper into understanding these methods, so stay tuned. So, what do we mean by determining the shortest path by inspection? Well, it's quite simple. This method is all about using our observation skills to find the shortest path between 2 points on a graph. Think of it as a visual puzzle where the aim is to connect 2 points using the least amount of steps possible. Let's imagine we have an unweighted graph. In this context, unweighted means that all paths between points or vertices are considered equal. There's no preference given to one route over another. Now, let's say we want to get from vertex A to vertex B. We start at A and look at all the paths that lead away from it. We then choose the path that leads us directly to B if there is one. If there isn't a direct path, we simply pick any path and continue the process from our new position. This process of moving from vertex to vertex is repeated until we reach our destination. The key here is to always aim for the path that brings us closer to our target. Remember, this method relies on the simplicity of the graph. With a small, uncomplicated graph, we can easily see all the possible paths and make our decisions accordingly. But what if our graph is larger and more complex? Well, that's where things get a little tricky. You see, the more vertices and paths a graph has, the more difficult it becomes to find the shortest path just by looking. There are simply too many options to consider, and it becomes more likely we'll miss the shortest path. So, while determining the shortest path by inspection is a handy and straightforward method for simple graphs, it's not always the most efficient or accurate approach for larger, more complex ones. That's how we find the shortest path by inspection. But what about larger, more complex graphs? For those, we'll need to turn to a more sophisticated method. Stay tuned to learn about Dijkstra's algorithm, a powerful tool for finding the shortest path in weighted graphs. For larger, more complex graphs, we need a more robust method. Enter Dijkstra's algorithm. This is a clever tool named after its creator, Dutch computer scientist Edsger Dijkstra. He developed this algorithm to efficiently find the shortest path between 2 points in a graph. And when we say graph, we're not talking about bar charts or pie graphs. In this context, a graph is a network of nodes or vertices connected by lines or edges. But Dijkstra's algorithm isn't just any algorithm. It's specifically designed for weighted graphs. Now you might be wondering, what's a weighted graph? Well, it's a graph where each edge has a certain weight or cost associated with it. This could represent distance, time, cost, or any other factor that adds complexity to the journey from one node to another. In contrast, unweighted graphs don't have these complexities. Any path from one node to another has the same cost, making it relatively simple to find the shortest path. That's where Dijkstra's algorithm shines. It takes into account the weight of each edge, tackling the complexity head-on to efficiently find the shortest path in a weighted graph. So, how does Dijkstra's algorithm work? It's a step-by-step process. First, it sets the initial node and assigns it a tentative distance of 0, while all other nodes get a tentative distance of infinity. Then, it considers all the unvisited neighbors of the current node and calculates their tentative distances. The node with the smallest tentative distance becomes the new current node, and the process repeats until it visits all the nodes. Finally, it backtracks from the destination node to the initial node to determine the shortest path. In essence, it's like a very smart GPS that calculates the quickest route to your destination, taking into consideration all possible factors like traffic, road conditions, and distance. Sounds complex? Don't worry, we'll break it down in the next scene. Let's see Dijkstra's algorithm in action. Imagine a weighted graph, a collection of vertices connected with edges, each edge having a certain weight or distance. We start at our chosen vertex. Let's call it vertex A. This is our starting point, and for now, it's the only vertex we know. The distance from A to itself is 0. Now we look at all the vertices directly connected to A. Let's say we have vertices B, C, and D. We note the weights of the edges connecting A to these vertices. These are our tentative distances. Vertex B might be 2 units away, C 3 units, and D 5 units. Next, we move to the vertex with the smallest tentative distance. In our case, that's B. We now consider vertices directly connected to B and not yet visited. If the path from A through B to another vertex is shorter than the previously known paths, we update our tentative distances. We repeat this process, always moving to the unvisited vertex with the smallest tentative distance, until we visited every vertex. At the end, we have the shortest path from A to every other vertex. This systematic approach, always choosing the next closest vertex, is the essence of Dijkstra's algorithm. It's like being in a maze with many paths, but always choosing the path that looks the shortest, step by step, until you've explored the whole maze. And that's how Dijkstra's algorithm helps us find the shortest path in complex graphs. To wrap up, let's quickly revisit what we've learned today. We've dived into the world of shortest path problems, exploring how we can determine the quickest route between 2 points by inspection. We've also unpacked Dijkstra's algorithm, a powerful tool used to find the shortest path in a Want to rise to your full potential in your studies and revise like a boss? You can trust Study Guide today to have you covered. Subscribe to this channel and see our website linked in the description of this video to see revision articles to maximize your study gains.